So this is a journey we are going through for last 3.5 years to update the ACPI specification. And today, I'm happy to share that it is ready for adoption. So here is the agenda. I am sure most of you are already aware of ACPI. But in case someone is new, I will give very quick introduction to the ACPI and why it is important for server class. And then we will talk about, go through some of the important milestones, what we achieved to enable ACPI for RISC-V. And then we will dive into the details about some of the important updates, what we have done for supporting RISC-V. Then we will compare the features of ACPI for RISC-V with other architectures, and acknowledgements and summary. I have a ACPI demo as well, a quick booting Linux kernel on QEMU, and finally question answers. Okay, so what is ACPI? ACPI stands for Advanced Configuration and Power Interface. So this is an OS agnostic specification maintained outside of any operating systems by UEFI forum. The key features it provides is device discovery, configuration, power management, performance management, thermal management, and also events and RAS. It is a set of interfaces between the operating system and the hardware. Basically, it is a set of tables, and tables can be either static tables in memory or a dynamic AML bytecode. So the advantage of AML bytecode is it provides the platform description, and the operating system can execute the methods which are encoded in AML bytecode in an agnostic manner. But operating system will need to have an AML interpreter to interpret this bytecode. But this is the major difference between the device tree and ACPI. And you can see the picture, the way operating system discovers the ACPI is through that RSDP, which is the root system description pointer provided by the firmware to the operating system, which is the root of this ACPI infrastructure. And it is provided through UEFI system table. Operating system discovers entire ACPI infrastructure using that RSDP. And the DSDT is an important table in the ACPI, which provides the dynamic namespace, which provides the control methods, what I explained. So why it is important for server class? So the AML bytecode allows the platform to encode the behavior. You don't have to change the operating system. So it has well-established bindings, especially for RAS across the CPU architectures. So operating system behaves in the same way for different architectures. It helps to break the dependency between the schedule of platform vendor versus the operating system vendor, especially in the enterprise class where there is larger window of operating system support. And it helps in support model and compatibility. And it's a single interface which works across the operating systems, including Windows. Okay, so these are the enablement milestones what we achieved. So in 2021, we started this effort under the World Platform HSE group. And in 2021 summit, I presented the early insights, what we need to do to enable ACPI. It was very early insight. And today in 2024, I'm happy to share that we have achieved that RISC-V completely supports ACPI. So between these 3 years, the top of this timeline diagram shows all the specifications, what we got approved. And while ACPI main specification is maintained by the UEFI forum, there are other specifications also which are required, which are maintained either by the RVI or by the other organization like Microsoft. So one of the dependency for us to, before getting this ACPI specification maintained, updated was the corresponding hardware specification from RVI has to be ratified. So because of that, we had to delay the AIA-related specification update in the ACPI. And so we divided the ACPI engineering change request to update the ACPI spec into multiple of that. So first we got the local interrupt controller and the hard capability table approved. Then we got the AIA once AIA was ratified. Then we got the SPCR spec updated, which is maintained by the Microsoft. And we also got updated FFH spec ratified by the RVI. And the NUMA support we added in 2024. So the bottom half shows that the upstreaming effort. So as soon as the ACPI specifications were approved by the forum, we basically upstreamed all the patches, both in QEMU as well as Linux. So you can see that different milestones where we submitted patches and upstreamed. And 6.12, Linux kernel is going to have all the support, whatever is required for ACPI. Sorry. OK, so let's get into what are the different updates we had to do in ACPI spec. So the first key thing is the interrupt controllers. So every architecture has different interrupt controller structures in the ACPI specification, which is discovered by the operating system. So this is a typical AIA interrupt controller architecture, what we have in RISC-V, which has IMSIC is a MSI controller, and the devices which are MSI capable can directly interrupt using IMSIC. Whereas APLIC is you can use it as a MSI, wired to MSI bridge. So devices which are not capable of MSI, which are capable of only wired interrupts, they can use the APLIC. So when we initially started this effort, we were focusing only on the server class platforms where, like Ved mentioned, MSI controller is mandatory. However, we also enabled the existing PLIC because even existing hardware can support the ACPI. So for developer options, people can use the existing hardware and add ACPI support on that. So we basically added all 4 interrupt controllers, local interrupt controller, MSI controller, APLIC, and PLIC. So all these change requests in the ACPI spec is approved. And we also need APLIC and PLIC in the namespace device, which is defined in the BRS spec. So 6.6 is going to have all these changes, ACPI 6.6 specification release, and QEMU and Linux latest already have these changes upstreamed as well. Coming to the hardware discovery, especially CPU information, this is something new in RISC-V compared to the other architectures, especially things like ISA string, what are the extensions supported. Discovering that through ACPI, we needed a new table for RISC-V, so we introduced something called as RISC-V hard capabilities table, RHCT. And this is very special table, which is only for RISC-V. It provides basically ISA string, CMO information, MMU information, etc. And in future, if you want to extend, it can be easily extended also. Again, this is approved, and ACPI 6.6 will have the changes, and upstream is also done. Another important aspect of ACPI is power and performance management of the CPU. So at high level, the CPU idle or low power idle, what we call in ACPI, is architected like this. The S-mode firmware provides the ACPI LPI object to the operating system, which provides all the details how to handle the power changes. And the driver in the Linux kernel CPU idle framework, as part of initialization, it reads those LPI objects and initializes the things. And at the runtime, when it wants to reduce the power, it can use it can decode those objects and call the SBI HSM call. SBI HSM has the suspend interface. Using that, it can control the power. And similarly, for the CPPC, this is for the CPU FREC driver. And this is another technology which is improved version of the P-state in Intel architectures. So again, the firmware provides the CPC object and CPU FREC driver and initializes that, and using the CPC object, it decodes that object and calls the corresponding handler in the SBI. So for these two technologies, the ACPI, CPPC and the LPI, the registers, the data can be anything. It can be either memory data register or it can be something called as FFH, fixed feature hardware. Fixed feature hardware is architecture specific, and each architecture maintains their own specification to how to decode that and how to handle that particular register. So for that, we had to introduce FFH specification, and we got ratified last year from RVI. So this is what FFH specification is ratified, and ACPI is also updated, approved. And again, it is all upstreamed as well. Okay, so a few more things like NUMA. For NUMA, we have two tables in ACPI for NUMA support. System resource affinity table and system locality information table. Both of them are mostly platform neutral, except we had to introduce one more structure for affinity of the local interrupt controller. That is introduced and approved. And for cache topology, processor topology information, we have PPTT. This is standard across. And again, this is also upstreamed. And secondary port console redirection table, which is basically maintained by the Microsoft. We added support for RISC-V and updated to the version 4. The BRS specs defines all the ACPI IDs required for UART. Again, all these changes are upstreamed. Quality of support, quality of service controller support, this new ACPI table, again, in different architectures are maintaining their own specification for this. So similarly, RVI is going to define this, and a draft specification is available, and next year, hopefully, it will be ratified and upstreamed as well. Next important thing is IOMMU. Like Ved mentioned, this is a key component of server spec. So for this, IOMMU, this one, operating system needs to discover the IOMMU and what are the devices behind that. This topology needs to be communicated from firmware to the operating system. So again, individual CPU vendors have their own table. So similarly, RVI is going to define a new table for IOMMU information. This is called RIMT. So this draft is available and POC is done. It is under architecture review. We have received some comments, and we will soon address them and probably go for public review on that. So basically, it provides the information how individual devices, PCI, for example, PCI devices, which IOMMU is handling those devices. So using that information, the operating system can discover that topology and configure the IOMMU. The another key aspect of ACPI and server spec is RAS. So we are supporting this firmware first error handling using ACPI's API framework. Again, standard across the architectures. We needed some changes for that, especially new high priority supervisor software events, like Anup mentioned yesterday in HC. So we had to introduce that. And POC is done, and which supports basic RARI emulation. RARI talk is there after this. RISC-V error record register interface. And we have RAS agent in OpenSBI, and EDK2 discovers this RAS agent. And creation and population of these ACPI tables in EDK2, and finally error dump in Linux kernel. So SSC and mproxy are RPMI are dependencies for this, and as soon as they are frozen, we will submit the UEFI ECRs as well, and next year we plan to upstream this. At high level, this is the architecture of RAS. As part of initialization, during boot, the error record, RARI error banks are discovered via DT from the OpenSBI, and EDK2 creates the HES table, and operating system discovers that, initializes the GH as part of GSGS driver. And the next, at the runtime, when error happens, the event will propagate to the M-mode firmware, and M-mode firmware will create the CPER error record, and basically using the SSE infrastructure, it provides the event to the Linux kernel, and kernel driver handles that and populates the error dump. And RAS daemon can save it into the logs. OK, so a quick glance about where are we with respect to ACPI. Basic discovery, all the standard tables we are supporting in RISC-V. Interrupt controllers, we have introduced whatever is required for RISC-V. Topology information, PPTT is supported. PCI is supported. Console, again, SPCR is updated to support RISC-V. NUMA, SRAT is updated to support RISC-V. Power and performance management, LPI and CPPC are supported, and FFH spec is ratified. And timer, we have this RHCT, which provides some of this information. RISC-V hard capabilities, like I mentioned, ISA string, we have this RHCT table. And there are some non-architecture specific things are there, like graphics, CXL, NVDIM, management, ISCSI, boot, PMU, everything should be supported. PMU is nothing is required, but everything else should be supported in RISC-V as well without any changes. So some of the advanced features like IOMMU, API, RAS, QoS controller are under progress. I mean, we are going to freeze very soon, and then probably next year it will be upstreamed as well. Yeah, so a lot of people have contributed to this. I should thank them. And via comments or feedback, everything. So many people have contributed. Thanks to them also. So in summary, RISC-V ACPI is ready for servers and other platforms. Both specification as well as upstreaming is done. And upcoming 6.6 release is going to have all the required specification updates. And it's fully supported in QEMU 9.1 and Linux 6.12 with EDK2. You can go and build and use that to experiment. The major thing is it enables some of the operating system vendors who are waiting for this because they are ACPI only. They cannot support with DT. So this enables them to start supporting RISC-V. And also advanced features like RAS, IOMMU, and QoS are planned to be in advanced stage, and we will complete it in 2025.